Alright, so we're going to get started on our Unit 1 notes here for probability and statistics. So our first unit is going to cover a bunch of vocabulary. So just kind of going through that. Looking at our first slide here, we're going to start with an overview. So in this unit, we'll cover a variety of vocabulary terms and concepts that will be needed throughout the year. So again, these are words that you're not going to be tested on necessarily throughout the year, but you will need them throughout the year just to kind of understand what's going on. We need to establish our linguistics. Cool fancy word there basically means we need to know how to talk about statistical analysis before we can do it properly. Again, it's kind of like a foreign language. A lot of these words are weird looking. And again, you can't understand what we're saying in statistics for the rest of the course without a good feel for this unit. Alright, so something we kind of talked about yesterday here, COL, so our 4 parts of statistics. So we're going to collect data, we organize it, analyze it, and learn. So one of the most tedious and time-consuming things you're going to do in any part of statistics is collecting data. For grad school, I actually did some research dealing with our feeder schools and like their grade equivalencies and math and all that. Even to download that data, which was collected by Stanford University, like it literally took me like 30 minutes on our web connection to download such a large file. In terms of sorting and getting everything to work through that, so organizing by grade levels, by different feeder schools, finding down different years of data. How you collect it, again, sometimes takes some time. That builds into the organizational piece. So whether you're collecting, if data is already accessible, if it exists, it's already been collected for you, obviously that's going to save you some time. But a lot of times when we have a new or novel idea or question, or if we're trying to sell a product, we have to collect our data on our own. So there's a lot of different ways we're going to do that, and we're going to talk more about the vocabulary about collecting in this unit. So this unit is going to focus pretty much all on collecting data, the proper way to do it to ensure that our data is valid and that we can move forward in our studies. Organizing, we'll talk more about in the next unit. That deals with kind of sorting the data, looking for trends, and displaying it, which kind of then builds into analyzing, and lastly, learning or making those conclusions from it. So our first big term here, data. It's the information that we gather. Data can be literally anything. Think of it as the answer to any question you can ask. All right. So again, if we think about it, we just want to think of data as the information we gather or we collect, and that's going to help us try to learn about whatever it is we want to discover. Oh, also, guys, I'm not going to lie, I picked a really predictable pattern for all of these like transitions. I'm not the most creative person, but there is those cool like transitions in the slides, right? Awesome stuff. Yeah, all right. Summer school. Woo. Okay, all right. All right, so next 2 things, individuals versus variables. Now, these may sound like terms you've seen before, but again, how we define them in terms of statistics, really important to us here. So, individuals are the people or the objects we are examining. So if I'm doing a study on toothpaste, and I'm talking about different brands of toothpaste, the individuals in that study might be people's teeth, they might be the different brands of toothpaste. It's all about how I define my structure. So if I'm saying which toothpaste contains the most whitening agents, then I would just be literally, my individuals are toothpaste. So I'm comparing Crest, Colgate, all these other various brands. If I'm saying which toothpaste helped prevent gingivitis in people or in users, then my individuals would be those individual people. That way I could go ahead and see, okay, this person had more, this person had less, so on and so forth. Looking at variables. So variable, it's the characteristic or the trait that we are trying to learn about or measure. So individuals can be, again, what we're looking for or who we're gathering our data from. It's the things we're examining. Variables is what we're actually measuring. So this is where we get into our 2 types of variables here. We have quantitative and categorical. So when it comes to these 2, basically if you can be really, really good at knowing one of them, by default, you know the other. So when you learn this originally, we always say, oh, quantitative, that deals with numbers, right? That's our most basic analysis. But you'll see in statistics, we sometimes come across things that are numbers, but they're not necessarily quantitative. Categorical, here's where we're going to kind of define our difference here. So categorical deals with where we can sort things into groups or categories based on some characteristic. So you would think of things like if I asked you what's your favorite color, the most common type of pet to have, so dog, cat, fish. reptiles, whatever it may be. So if we can sort things into category, the most frequent or the most popular item, but we can't find the mean, that's how we identify something as categorical. So when we can find the mean of data, if it would make sense and give a meaningful answer, it's quantitative. So height, weight, any type of measure of things, so distance between things, how long something takes, anything to deal with that is going to give us quantitative data. Lied. It was not on this slide. Thought it was. So let's go back to that. So categorical stuff that looks like numbers. So things like social security numbers, phone numbers, street addresses, zip codes, all of those things are numbers, but they're descriptions of a location. So if I gave you 5 different phone numbers and said, what's the average phone number? You could treat them as values, add them together, but the answer wouldn't make any sense. It's not like you could find the average among 5 people. You could find the most frequent area code. So I could say, what's the most frequent area code of students in my classroom? Might be 708, might be 815, might be 630, depending where you bought your cell phones at. But, again, it wouldn't make terms in finding that mean. So when you look at the type of data, if you say, can I find the mean, would it make sense? So categorical data, if I took a bunch of zip codes, bless you, or social security numbers, I could add them together, but that data wouldn't tell me anything. Bless you again. Population versus sample. So this is where we start kind of dissecting like what it is we're talking about in a study and what it is we actually look at in a study. So a population is the larger or overlying group we are studying. So if I wanted to make conclusions about students here, I would say I'm studying students at Joliet Central. If I included West, it'd be students at Joliet Township. Now, would it be practical if I wanted to know the average height of a student in our school, Joliet Central, to measure every single student? Right, so it would probably be kind of time consuming, right? A good example is if I tried to do it in a week-long period, some people go on vacation, some people are late to class. I don't have unlimited time during my day to walk around and do this stuff. Some people might refuse. They may choose not to participate. So there's no way you're ever going to get all of the information on a sufficiently large population. So if you're looking at any larger group, it's really inconvenient to do the entire population. What that's known as is a census. So a census, like you hear the U.S. Census Bureau or U.S. Census, they try to do it every couple of years. Go out and gather all this information about our population, just so our demographics, all the data we can pull from is as accurate as possible. So when you're thinking about populations, always think of that larger or overlying group that we're trying to learn about. Now, sample is one of the biggest terms we're going to cover in here, and we're going to cover it for kind of the rest of the year. And it's also the part where things can go wrong when we're gathering our data. So the first idea about a sample is it's smaller, right? So if we're going to talk about students at Joliet Central, I'm not going to survey every single student. I'm going to look at a sample. Now, how I get that sample, what that sample looks like in comparison to school, that's where you can immediately decide if a study is valid or not. So, key idea here, the representative chunk of the population we gather our data from. So the word representative is the big one here. Chunk is just my version of saying group, portion. I just think chunk sticks in your head better, so I use that one. But representative is the big one here. So what that means is that the characteristics of the sample match up to the population. So again, kind of going with examples here, age, gender, location, whatever variables you want to match up with, you want to make sure that your sample looks like the population. So if I was going to study students at Joliet Central and I only interviewed senior males, would that be representative of our school? No, not at all, right? I'm only interviewing males and I'm only interviewing seniors. There's 4 years of students here. Also, they're not all guys. It's not a boys' school. So what we need to do here is make sure it looks the same. If I interviewed only Hispanic students, would that be representative of the entire school? No, right? Not everyone in this school is of Hispanic descent. So, the key idea here is that your sample needs to look like the group as a whole. So things I would do before I gather a sample is I would go ahead and look, we showed early in class that Illinois school report card. So I'd go on there and I'd say, hey, what's the demographics of our school? Okay, it's this percent of each race or ethnicity. All right, what's the male to female ratio? get some ideas about how you want your data to look when you move forward. That way, when you're sampling, you can see how big of a sample you need to get to kind of mimic that as best you can. So you want to get the different ages. So if I was talking about the whole school, I'd want to have freshmen, sophomores, juniors, and seniors. I wouldn't want everyone to come from the same grade school. I wouldn't want everyone to be all people who are working. You want to cover everything. So anything you can do to make your sample mimic or represent the population makes your sample that much better. Most major studies that are debunked for various countless reasons, a lot of it comes back to their sampling methodology. So for example, if you're talking about political polling, have you ever looked at an election map? Probably, maybe you've seen one on the news, right? So certain states, certain districts, certain counties have historically always voted primarily Republican or primarily Democrat. So if I was trying to gain a fair and unbiased sample of an election poll, would I want a sample from a place that has voted the same way for 50 years? Probably not, right? That's not going to give me a fair opinion of everything. I'd probably want to mix my sample between one place that always votes Republican, one place that always votes Democrat, a swing state. You'll hear about those a lot in the election times. So you'd want to gather a sample from a lot of different locations, people from different economic backgrounds, different education levels, different genders, age, ethnicity. The more it matches up with your population, the better sample you get. So again, if you look into a lot of those polls, sometimes people look into them like, wait a minute, you only sampled this area and it's been this way for so long. So again, and that's not just in politics, that's in everything. That if you look at the samples people take, sometimes it changes the validity of their study to a certain degree. All right, our next big thing to distinguish between is a parameter versus a statistic. So what's weird is that they're kind of the same thing, it's just which one we're talking about. So we're going to hear descriptive statistics a lot. So we're going to talk about means, we're going to talk about average, we're going to talk about trends in data, standard deviations, variance, all these different words we'll get to throughout the year. A big thing is that we need to know what we're talking about, whether it's a population or a sample. So what's cool is the letters actually match up. And I don't know if that was intentional or just a coincidence in our language, but it works good. So parameter, population, both start with P, right? Statistic goes with a sample. Both start with S. So they match up, and that's kind of cool about it. So first I'm going to talk about as a parameter. These are characteristics about a population that are already known. So for example, the easiest one to think of, if I think about all of the different ways I could flip a coin, right? The probability of a coin landing on tails is 0.5. Now again, in probability and statistics, we always list off our assumptions. So if I were to make this sound like a test problem, I'd say if I flip a fair and unbiased coin with the two outcomes of heads and tails, what's the probability of heads? Stats problems, kind of textbooky, they always sound way more like in-depth than they need to be. So when we're talking about probability or any kind of event, we always assume it's unbiased, it's fair. I didn't weight the coin, it's not like severely dented on one side. It's a normal coin that you would flip. The other one you can think about, population, approximately. So being 50% female and 50% male, depending on your current definition of that. But like just in general, again, rounding, so type thing if you include other genders into there. It's just a good way of visualizing it. So again, these are characteristics about the population that we kind of know ahead of time. So if you can think of those things, if they're sort of facts about our world that we live in, again, those are considered parameters. So if it's about a population, it's a parameter. So again, P and P. The one we will work with about every single time we try to do anything in statistics is a statistic. So it comes from a sample. So in both these, I could have, let's say I had a parameter about the average life expectancy, right? So over 100 years we've collected this data. It's pretty standard. It's not fluctuating a whole lot. Say that the average life expectancy, and I'm going to be honest, I don't know this offhand, so I'm going to throw the number 80. Like let's say the number is 80 years. That's how long you're expected to live. That's considered a parameter because it's coming from the population as a whole. There's a lot of longevity to the study. There's enough data to establish it as a parameter. Now a statistic would be as if I looked at one town. So if I looked at just Joliet and gathered data over the last 10 years and seen life expectancy. That would be a statistic because it's derived or comes from a sample. Now, about these things is they kind of sound the same. It's all about where it comes from. So my statistics, I'm looking at a sample mean, sample standard deviation. So basically anything we calculate and aren't given. So if you plug something into GeoGebra, you plug something into a calculator, you are calculating a statistic. You are never calculating a parameter. Those are kind of things that are found through longitudinal studies and again, like just kind of developed through history of humanity essentially. But in general, statistics are what we calculate. So anything you calculate in this course or anything you probably calculate in your life is going to be a statistic. Key differentiation there is that parameter, population, so P and P, statistic, sample, S and S. All right, let's get through one example here, and then we'll move on to the rest of these notes a different day. So we have television station. Q wants to know the proportion of TV owners in Virginia who watch the TV station's new program at least once a week. The station asks a group of 1,000 TV owners in Virginia if they watch the program at least once a week. So take a second right now and look at those three parts of the question they're asking us. We're looking for a sample, we're looking for the population, and is the variable quantitative or categorical? Now there's no defined order. This isn't like your algebra type test where it's like, if you don't do part A, you can't do part B or C. You can answer these questions in any order. That's kind of what's cool about stats is that like it's more so like you could do any order you want right now. So again, take a minute right now, kind of jot down what you think is going to be the best answer there. Alright, so looking at our first one here, we're identifying the sample and the population. So what we want to think about there is what's the big group we're talking about, and then how many people or what chunk of that population am I actually working with to get my sample. So who are or how many people did I actually gather my information from? 1,000, right? So things we want to be with samples, we want to be as specific as possible. Now, like I said, what's cool is all your guys' tests are on a computer. So like typing is super fast, right? So if you want to take notes in a computer on a Word document, however it works for you, I will never check in your notes for any type of credit. But again, I'm going to be a little wordy with a few of these just so we get the trend down. So for this first one here, we have identifying the sample. So we had 1,000 TV owners in Virginia. So our sample, 1,000 TV owners in Virginia. Now we can officially see why I usually type things. My handwriting, not the best. True. I can't even blame it on the computer. It looks worse on paper. Alright, so that's our sample. So again, specific as possible there. Now again, if you give me just the number 1,000, I kind of know what you're talking about. But in statistics, we need to be specific. Like I said, the advantage of not having a whole lot of work to show mathematically, calculating-wise, is you need to be specific from the problems. Now, am I going to give you 100 of these in your homework? No. Am I going to give you 100 on your test? No. But what I'm asking is when you do a problem, do it the correct way. All right. Now, that's a sample we took. Why would I not want to include people in here that don't own a TV? Exactly. I know what their answer is going to be. 0, right? Also, I'm noticing that they're looking at the proportion of TV owners. So, if someone doesn't own a TV in Virginia, they're not even concerned in my sample. I know my show isn't going to be watched by them. So we're only looking for people who are valid in our little marketing scheme here, the people that we want to target. All right, the population. So we looked at the sample. We found out who we looked at. Now, what's the larger or overlying population? Not just Virginia. We look at our sample. So I had 1,000 people. What's the big group? TV owners in Virginia, right? So we just take away the number. So in a lot of cases, I know that sounds like an algorithm for it. So we're looking at 1,000 people, and that overlying group that we want to know about is all TV owners. Exactly. So we're looking at that sample, and we want to make a conclusion about all TV owners in Virginia as a whole. Whoa, that was. Hold up. We lost a couple slides here. Let's go back to where we were. There we go. TV owners in Virginia. Yeah, Yeah, no. We're going to start typing with the next set of notes. Guys, I'm sorry. This is brutal handwriting. I'm going to blame the pen, even though it's not the pen's fault. All right. Last thing. So we looked at our sample. It's 1,000 of these people, and we want to learn about all of them. So that's our population there. Next thing. Is the variable quantitative or categorical? Now, what we're looking here, we're saying, do they watch it at least once a week? So think about your possible answers for that question. So I'm going to ask you guys right now, do you watch Netflix once a week? Now, I heard answers like yes. I heard answers like no. Did I hear an answer of 7? No. Now, if I asked him, how many times a week do you watch this? 7 days a week, 2 days a week, 3 days a week. So it's about what you're asking. So I gave this there's kind of a dichotomy here of answers. That's a cool sounding word. So dichotomy, it's another variation of, so D-I, B-I, bi, meaning 2 possible outcomes. So dichotomy, anytime you have 2 possible outcomes to something, it's categorical. So you either do watch it at least once a week, so that means once a week, twice a week, 1 billion times a week, whatever it is, or you don't. So since we have 2 possible outcomes, this is going to be a categorical question. So just kind of decide only yes or no answer. Say response. All right. So where we left off at last time was just kind of going through this first example here. We identified the sample, the population, and then the type of variable, whether it's quantitative or categorical. Moving forward, our next set of vocabulary terms here is levels of measurement. So the 2 levels of measurement we're going to start with are dealing with nominal versus ordinal. So levels of measurement, it refers to, it doesn't necessarily tell us which type of data we have. We kind of look at it first and then make our conclusions from there. So the first thing we need to consider is what we can do with the data. So can I sort it? Can I order it? Can I find calculations with it? So our first one here, nominal. This applies to data that consists of names, labels, or categories. The key idea, there is no measurable order to the data. So if I gave you a list of types of shoes we have in this classroom, I can maybe find the most frequent one, but there's no way I can rank them in terms of preference or order. It's not like one finished before the others. So we can't say that, Adidas beat Nike by 5 minutes. That doesn't even make sense when we think about it. So anytime you have data that's essentially just giving you a list of labels, a list of names, with no discernible characteristics, that's when we're at the nominal level. Now, nominal makes a lot more sense once we consider what ordinal is. So ordinal, this is similar to nominal in the sense it's categorical data, but it can be quote-unquote ordered. So both of these deal with solely categorical data. So again, anytime we have data that's non-numeric, we can't find the mean, it's going to be either nominal or ordinal. So the difference with ordinal is, again, we can kind of rank things. So think of place finished in a race. If I had a list of, okay, the different places something finished in, so most popular items, okay, so there was the most of these. There was the second most of these. There was the third most of these. So again, anything you can rank, or letter grades is another great example of that. Again, you can't add letter grades together and find the mean, but you can rank them so an A is preferable to a C and a D, so on and so forth. So again, if you could put it in order, if there's a preferable outcome, it's ordinal. If it's just a random list of words, essentially if it has no order to it, then it's nominal. Our next 2 levels of measurement. So this is interval and ratio. Key idea here, we moved up to quantitative data. So if you have anything quantitative, so if I give you a list of heights, a list of weights, a list of times it took to complete a given task, you are automatically at one of these 2 answers. If I give you anything categorical, it's either nominal or ordinal. But again, if you have quantitative, you're either interval or ratio. So how we distinguish the distance between these, or the difference between these, is based on one concept. And again, depending what textbook you read, what professor you have, there might be more they add to this, but this is kind of the key idea here. So interval. So with interval, it's quantitative data, and it makes sense to add and subtract values. That's kind of the textbook definition. The key idea here is that it doesn't have a true zero, meaning lack of a quantity existing. So, I know that sounds like a lot to wrap your head around. Ratio is really, really similar, but it has a true zero, so such as distance. So when we consider these things, that's really and again, I'm not going to give you guys test questions on this as much. It's more so just I want you to have a basic understanding. All right, so again, some examples here. If we look at that ratio level, we're thinking about distance. If two people are standing right next to each other, there is zero distance between them. So in that sense, it'd be ratio because there's a true zero. Things that don't have a true zero, if we think about the Fahrenheit scale of measurement, right? It can be 0 degrees outside. Well, where we live, that happens like, once a week in the winter or lower. But it's not lacking temperature. So it could be 0 degrees out, but there's not a lack of temperature. It's just a marking spot. Similar, like, okay, for example, ratio would be test scores. You can get a 0 on a test, meaning you literally didn't get anything right. Obviously, none of you would ever do that in my class. But again, it's theoretically possible. Things that would be interval level would be, let's see, another good one here we could think of. So not having a true zero would be age. Thank you, Rosa. Age is a great example of interval because there's no true zero, meaning the second you're born, by default you have some type of age. Even though we'd say 0 years, again, because time never technically stops, you can always measure it in some sort of thing. So again, there's no zero there in age. So again, the key idea with levels of measurement is being able to distinguish quantitative. Okay, it's definitely either interval or ratio. And I'm more so concerned with your explanation as to how you interpret whether there's a zero or not a true zero. And then when we get to those categorical ones, those are much easier to distinguish between nominal and interval. Or nominal and ordinal, I should say. All right. Now, we have some data. We're going to deal with discrete versus continuous. So, discrete is the only one that can go either way. It can either be categorical or quantitative. So when we think about discrete things, that means there's only a finite number of choices. So if it's categorical stuff, we could think of it being multiple choice. So choose A, B, C, or D, true or false, yes or no. So again, multiple choice options, that's our categorical. So categorical data is never going to be continuous because there's only going to be a finite number of answers. If I asked you to name every first name you've heard, eventually you'd run out of options. So it's still categorical because again, it's sorting, it's grouping, it's an identifying characteristic. A quantitative example of discrete would be looking at only whole number answers. So again, a finite number of answers. Think of no decimals. There's no continuity between choices. So if I gave you a multiple choice test out of 10 questions, you could only get 1 right, 2 right, 3 right, all the way up to 10. So that means, again, you can't get anything in between if there was no half credit assigned. It's multiple choice, you're right or wrong. So discrete, just think of there's no connection between numbers. It's one or the other. For continuous, this one is always going to be quantitative. So here we want to think of that thing you wrote 1,000 times in advanced algebra where we wrote all real numbers, right? For domain and range of all that functions and stuff in that unit. There's no stopping it, so there's no jumps between numbers. Great examples of things that are continuous. Height, weight, time. Kind of your go-to when you think of like different variations of quantitative data. Those same examples we always hear about, those are always going to be continuous because there's no gaps. So if I'm measuring distance, it's never going to be exactly 1 mile. It might be 1 mile and 1/10 of an inch or whatever it may be, however close we can break that down. If you're using a stopwatch, right? Technically, those decimals go on forever, even though it might say 10 seconds, 0.132, depending on how good your stopwatch is. It still technically goes on forever. So again, infinite decimals, that whole number line. So if we're measuring weight, even though a scale might, only show pounds, again, if you get like a different type of scale, again, you can see those decimals in there as well. So anything that you think of like height, weight, age, all those things are continuous data. Whereas again, categorical, if I said, okay, how many siblings do you have? That would be discrete because you cannot have a half of a sibling or a third of a sibling. There's only a set finite number of answers. All right, next example. We're identifying whether things are discrete or continuous. So for our first one here, If Taos, Acoma, Zuni, and Cochiti are the names of 4 Native American pueblos from the population of names of all Native American pueblos in Arizona and New Mexico. So, is this going to be discrete or continuous? Discrete, right? There's no, I can't add and subtract these names. It's just, again, it's a random sort of list of names. So, what that gives me is discrete. Next one, in a high school graduating class of 319 students, Jim ranked 25th, June ranked 19th, Walter ranked 10th, Julia ranked 4th, where 1 is the highest rank. Discrete again, right? So this one, again, we're just measuring rank. You can't rank 1.5. So again, because there's a set order to it, there's a set number of possible outcomes, this one's going to be discrete as well. Body temperatures in degrees Celsius of trout in the Yellowstone River. Continuous, right? Because depending on how accurate of a thermometer I may have, again, that's going to be continuous there. We can get those things in between. It's never going to be exactly 10 degrees Celsius. Length of trout swimming in the Yellowstone River. Continuous, right? Because when you measure that, again, first off, rule of thumb when you fish, you take the picture farther away from your face, right? Looks bigger because of the distance in between. Angles make fish look bigger. Other sides of that is, again, it's that continuous concept, right? It's never going to be exactly a 1 foot long fish. It can be a little more, a little less. So we're always continuous there with those types of things. All right, so something else I want to do here. So we have discrete data for the first two. So we're going to go ahead and rank those now as whether they're nominal or whether they're ordinal. I should have also put that in directions. Honestly, just forgot to type that in there. So for the first one, we have these names of different people. Is that going to be nominal or ordinal data? Nominal, right? Again, it's information. It's great to know, but I can't really put it in order. There's no preference when it comes to names. So that would be nominal data for the first example there. Looking at our second one. So again, right here, we have a discrete type of data, so we know it's either nominal or ordinal. So if I'm looking at this one, is this one going to be nominal or ordinal? Ordinal, right? Because it's giving me rank. So they're identifying there's a preference. 1 is the highest. Again, we're putting things in order. So that one would be ordinal. All right, now these next two, again, we're just going to kind of walk through a little bit of justification. So we see right now we have continuous data, right? So we know it's quantitative. And if I have quantitative data, by default, I know I'm either at interval or ratio. So for the first one here, we have body temperatures of trout in the Yellowstone River. Now, is there a true 0 in terms of temperature? No. Not in any scale you're ever going to use. Technically, one exists in Kelvin, but I will never actually test you on that. That's like the absence of temperature. It occurs in some parts of space, etc., etc. Fun sciencey stuff. I'm never going to test you on that. So if I give you anything about temperature, again, there's no true 0 in any typical measurement system. So here, that's just going to be interval, because interval does not have a true 0. Last one, length of trout swimming in the Yellowstone River. Now, with this question, I would honestly take either answer, because again, technically length does have 0. If it doesn't have any length, it's 0. But typically, if you're talking about fish you're catching, it wouldn't really make sense to say 0, because that means the fish doesn't exist. So for this one, if I gave you this on a test question, I would take either answer, and I would be grading it off of your explanation. So if you said, oh, well, you know, if it had a length can be 0, therefore it's ratio. Or you could tell me that, hey, I couldn't catch a fish of length 0, so therefore it's interval. Either way that you rationalize this one, I would take it. Let's get through 2 more slides here, right? Okay, example 3, we have quantitative or categorical. So here we are looking at area codes. Is that going to be quantitative or categorical? Categorical, right? They're numbers, but I can't find the mean. So that first one there is categorical. Looking at our next one here, brand of shoes. Categorical, right? Again, I could sort them. I could say, okay, these brands are the same, or there's more of these, less of these. But again, we can't find the average brand of shoe. Weight. Quantitative, right? I could definitely add and subtract those, find the average. Number of students in this room. Definitely quantitative, right? I can count you guys. It gives me a number answer. I could take the average over several class periods. I could see what my attendance is on average in second period. All right, we'll do 2 more slides. Actually, these are pretty quick. All right. Now we're looking at nominal or ordinal. So again, if I have nominal or ordinal, by default, I know it's categorical data. And now I just need to decide if there's an order to it. So the alphabet. Ordinal, right? We have a definition of the beginning and end of our alphabet. Therefore, ordinal. Types of clothing. Nominal. Brands of suit. Nominal, right? Because again, can't order those. Place, finish, and erase. Ordinal, right? So we got. There we go. That's an N. Yep. I'm gonna blame this pen. Just 100%. It's probably the pen, not my handwriting. All right. So it's ordinal, nominal, nominal, ordinal. For those of you who have yet to become used to my handwriting. All right, last slide for the day here. Okay, now we're looking at discrete or continuous. So again, similar to what we've done before, just breaking it apart here. All right, so number of book copies sold. Discrete, right? Can you sell half a book? No, right? It's whole quantity. So I may have sold 10,000 books. But again, you can't sell like the front cover and then the last 3 pages of it separately. People are going to buy a book, they're going to buy it in whole quantity numbers. So that would be discrete. That looked better, right? That was a little more easy to read. Got this. Progress. All right, time spent running. Continuous, right? Because again, it's not going to, you can't be like, oh, I'm going to run for exactly 8 minutes. It's not going to work. Amount of fluid in a glass. Continuous, right? So again, in all of our science classes, especially chemistry, you got to like lean down and you try to make it exactly right. It's never going to be perfect, again, because imperfections in the glass, whatever it may be, you might pour a little too much. Continuous. How many cards are in a standard deck? Discrete. Also, how many cards are in a standard deck? Fantastic. We know that answer. All right, so this is where we left off last time on slide 14. So we're going to go up forward here. Bless you. We have definitions for data collection. So a lot of the questions you've seen looking through your practice packet have to do with things of different sampling methodology, whether we're talking about an experiment or a study. And this also gets into the rest of our terms of bias and different issues we can have with our sampling. So, bless you. For our first one, we have a designed experiment. So these are the 2 different first steps when we're going to collect our data, designing what type of study or experiment we're going to work with here. Technically, there's a third that's known as surveying, but I really don't include it in here because that's just kind of a method for collecting the data. These are how we're going to do our whole thesis, experiment, whatever you may call it. So a designed experiment. Here, there's a clear purpose to our data collection. We are currently involved, we are actually involved in the collection process. Think of studying new medical treatments or seeing if training programs improve athletic performance. So, things to think about in here. Alright, so when we're thinking of these designed experiments, the key idea here is we are involved in what's going on. So we aren't merely observing, we aren't just pulling data that someone else did already. We are actually going to collect our data. We are affecting the situation. So in a designed experiment, you are a part of the process in that you are inducing or you're putting something in this environment. So medical treatments, anything about testing different drugs or different outcomes, seeing if a training program, so again, you're telling them to do something different. So if you're affecting the patient's or the subject's behavior, this is a designed experiment. Whereas with an observational study, here we have no effect on the environment. We are just watching and recording. So again, if data has already been collected, we're kind of pulling that down already. So it's just a study. We're looking at what already exists. Or if we're recording data, so we're getting new founded data, but we're not affecting it. So from a teaching standpoint, I could look at this 2 ways. If I want to do an experiment to see if having a review for a test benefited students, I might give half the students a review, and the other half would have none. So I'd have one group getting a treatment, which would be the review, and the other being a control group, so not having that treatment. If I wanted this to be an observational study with students, Perhaps I would just say, okay, hey, you guys have the day to review. Good luck. I would not leave my desk. I would not talk with any of you. I'd just be recording what happened. So, certain students were studying, others were on their phones, some were doing other homework, whatever it may be. So in an experiment, you are involved. You are changing the environment. Observational study, it's either data that's already been collected or you're just looking at it. So you're just watching what happens and recording. So here's where we get into our different sampling methods. You did see the majority of these in Unit 1 of Advanced Algebra. I had taken that class last year. The difference here is we're just going to go a little more in depth and kind of be able to distinguish between them, as well as decide which ones are kind of preferable if we're able to do the study correctly. So the first one we're dealing with is what's known as volunteer. So our first two, volunteer and convenience, are both pretty similar. There's slight differences, so in a lot of cases, either one will work depending on your explanation. But again, let's just start with them being as unique items. So an example of this, a radio host asking for people to call in and voice their opinion. Now, volunteer essentially means that you're asking for people to participate in your study. So you're not collecting people, you're not sorting them, you're just on the phone saying, hey, who wants to help? It's similar to a teacher calling on students in class and saying, does anyone know this? So I'm not using a random name selector. I'm not choosing any of you in any type of pattern. It's just whoever offers up their opinion. So why would this not be the most representative sample? So the types of people who respond to a volunteer thing probably have one or the other really strong opinion. If you have no real strong feelings, you're kind of neutral about something, chances are you're not going to give up your free time to call into a radio show host and talk on the phone about it, or tweet about it, or whatever it may be. In general, you're only going to get the one extreme and the other extreme. This is similar to when you have, like various newscasters, like they bring in people to talk about anything political, right? It's never the average person coming in. It's someone with one extreme view or the other. So again, when you volunteer these samples there, it's like you usually don't get the majority of people involved. And again, it's kind of far one way or far the other way. Our next one, convenience. I'm going to survey only my students who are present today. So this concept is, it's convenient for you. So maybe you're someone who plays on a sports team. So if you're only going to survey other people on the sports team, it's convenient for you because you're around them. Same thing if you only survey family members. This is an example of the sampling method we used on that activity in class where we found, you guys asked a question, you found some descriptive statistics of it. It was convenient because it was all people in the classroom and they were told by me to respond. Therefore, nice and convenient. So, why would this not be the most representative? So again, because it doesn't necessarily look like our entire population in question, not always the best sampling method there. Alright, so as we move up a little bit here, we get to systematic. So systematic, this is one of the easiest ones because you think of system, right? Like computers, it follows a pattern. So we're sampling every nth person that enters a given location. So think of this as, okay, I'm going to stand at the main entrance and every 5th person, every 10th, every 20th, whatever if person, or second or third, so technically entered or en-ist, whatever you want to call it, it's a pattern that you're following. So that enters into a given location. So this one is valid for sample generation, but could be challenging. So with this, there's something that's known as a non-response. So that's someone who chooses not to participate in a given survey or a given data collection method. So if I'm trying to get a sample of, say, 100 people and I'm standing at the door, if I'm sampling every 5th person, that means I'm going through 500 people and asking them. Say 100 of them say no. Now I'm going through a lot more people. Again, because I'm following that pattern of every 5th, every 10th. To make this sampling method viable, you can't change it midway through. You can't be like, forget it, I'm just going to do the next 20 people in a row. It loses its ability to be random and representative. So, again, it's valid, but it could be very challenging and time-consuming to do your sampling this way. Alright, here's some more that are also valid. So, simple random. You'll see this abbreviated as SRS in like a lot of stats problems. So again, this is kind of our most basic sampling method. So we want to think of put everyone's name in a hat, pick of, that should say pick off, or out. That should say a lot of things that aren't that. Pick out, bless you. There we go. Let's make it pick out. Okay, pick out however many you need. So that's the most basic one. So probably the most common practice for sample generation, but using computer programs as opposed to a literal hat. So the names in a hat, again, that's kind of like the way to visualize it, but never in real-world statistics would you actually put names into a physical hat and pick them out. You wouldn't fold up paper, so on and so forth. That's more of a primitive way of thinking of it, but like I have a random name selector thing here for you guys. If we ever need to utilize that, which we will later on. Same concept. So everyone has an equally likely probability. So those are the key ideas there of randomness. So all participants in a given population have an equal chance of being chosen. So if I'm putting those names in that list, I put each of your names in one time. If I were to put someone's name more than once, it wouldn't be random because they would have a better shot at being chosen. Again, that's probably the most common one you'll see. Most problems are like in an SRS, so simple random samples, so on and so forth. All right, these two. These are the most often confused sampling methods on the planet. So the one thing that they both stand out from the rest of the group here is that they involve creating groups prior to sampling. So each of the other ones has like a set methodology for how you're going to get your sample. These two involve groups. So for our first one, cluster. Creating groups in a population, then choose X of those N groups and ignore all the others. So right now, put your hand up, all 5 fingers. Promise this will help you remember. Okay, so I have groups, right? So the word problem might be like, all right, we divided students by grade level, or by English and math class, or by first period class, or we divided into male and female, into various your race, ethnicity, however they made groups. Or they might have just said, I randomly selected groups of 100, right? If there's some type of grouping involved, you are in one of these two options. Now, put down 2 fingers. Any 2. Okay, that's cluster. So, I had 5 groups, I chose 3 groups. It's cluster. So I ignored these 2 altogether. Everybody in these, they are now my sample. All right, put all your fingers back up. I made groups. Now I take some from each group. That's stratified. So the way to think about those 2. Cluster. I make groups and I say, okay, so right now your classroom's full of pods. You guys put your hands back down. It looks cool. I appreciate it. We all have questions. All right. Right here. So I have 5 groups, right? So I've grouped my students. And I say, okay, I only want these 2 tables. That would be cluster. Now, stratified would say, okay, 1 person from each table stand up. So you don't have to literally do that. But again, stratified, you have groups. You take some from each. So approximately an equal amount. It doesn't have to be exact. It's not like you have to say 1 from each or 20 from each. As long as they're close, you're good. And again, clusters, you make groups, and then you say, okay, the first 2 groups come up. Everyone else, you can go home. So however you remember the difference between those 2. So in a study, so at these initial stages here where we're trying to gather the participants for our data collection, there are 2 types of errors. We have either a sampling error or what's known as a non-sampling error. So the first one that we can usually defeat by picking a good method here is going to be a sampling error. So we just covered our sampling methodologies, our sampling techniques. Here's where those can go wrong. Essentially, anything we find in our study is useless and invalid since the way in which we generated our sample was flawed. So, like we talked about before, if your sample isn't good, nothing that you can prove or you think you found statistically means anything because your sample isn't what it was supposed to be. So the 2 most common things here are known as undercoverage and your sampling frame. So undercoverage basically means you don't have enough people in the sample. So there's rules of thumb we'll learn later on, but basically it's saying your sample is too small to actually have enough people in it to make a conclusion from. So that's like if I'm trying to do something longitudinal. I say, okay, I want to look at the past 10 years, but I only have data from the past 5 years, right? It's undercover. I can't actually make conclusions about a 10-year period if I only have things to back me up over 5 years. Again, same thing too. If you're looking at millions and millions of people, but you're only covering a small amount of that. So if you only got a couple different people in that, you simply don't have enough. The other one that's more likely to happen, undercoverage is pretty easy to fix once we move into that. Like you literally just get more people kind of thing, or more objects, more samples, take a little longer to gather your data. The one that's kind of a challenge and more common of a mistake is your sampling frame. So our sample wasn't representative of the population. So if we're not representative, our sampling frame's off. So again, if we want to talk about all students here and I only interview my students, I don't teach everybody in the school. So again, it wouldn't give everyone an equal likely shot. And again, my samples would not represent the population. They would not have all grade levels, all genders, and a variety of other variables to include in that. So again, if it's not representative, it's your sampling frame. If it's too few people, it's undercover. So the big one there I'd like you guys to be able to understand and explain would be the idea of representative. So if you could explain why a sample wouldn't necessarily match up with the population, you'd be good there. For our other way things can go wrong, so non-sampling errors. In this scenario, we did generate our sample through valid methodology, meaning I picked a good sampling technique, it's representative, all of what I've written down is good. But something still went wrong. So non-sampling errors are more, if I was trying to show one of these in the study, these are a little more nitpicky, I guess you could say. It involves a lot more thinking involved. So the three most common are going to be bias, the interviewer effect, or what's known as a lurking or confounding variable. So bias is the first one. Now let's say I want to show that everybody's favorite academy is health and medicine, because that's my academy. Again, they're going randomly there. So if I walked up to all of you and said, wow, isn't health and medicine the best academy? There's a lot of bias in that question, right? I'm ensuring to you that there is a correct answer to that. I'm saying, isn't it the best? So to say no, you'd be like disagreeing and all that stuff. So if you're implying in your questioning that there's a single right answer, and again, we'll cover more bias as we go on here, that's not how you want to ask questions. Questions need to be neutral. They don't need to have any strong words. They need to be as bland and as emotionless as humanly possible. So if there's bias in the way you collected your data or questioning, or you intentionally only interviewed people with a certain background or a certain level of knowledge on something, again, that could be some uninherent or unintentional bias. The interviewer effect refers to the fact that you might respond different to people depending how they look, how they act when they're asking you questions. So chances are, if a friend asks you a question, you'll probably respond differently to them than if an authority figure asks you a question. So whether it's your parent or guardian, if it's a police officer, teacher, especially if it's like the principal and they ask you why you're not wearing your ID, right? Probably going to respond a little better with an excuse there, instead of just asking for a time. So, again, interview effect, how people ask you the question or who they are. If you look up to them, for example, if someone was a role model to you or like a celebrity, you might answer them different than if it was just someone on the street. A lurking variable, or we can consider this what's known as a confounding variable. Basically, this is like it's something we couldn't foresee. It's something we couldn't predict. It's if you were asking people about, I'm trying to think of a good example. Okay, so, all right, so if you want to think about income level, right? You can take 100 people with a six-figure income, meaning they're making over 100 grand a year. Now, what could be a lurking variable in that is, some people kind of walk into jobs. They're lucky, their parents or guardians owned a company and kind of gave them a job. So they may have no educational level, but still attain to that income. So if you want to do a study of what, a level of education is most likely to attain you a very high level of income, lurking variables in that or confounding variables could be like, again, their family's socioeconomic status, where they came from, maybe they won the lottery. So again, lurking variables are things kind of in the background that we can't control. So those are things you kind of consider just a little bit when you're designing your study. All right, going a little bit deeper here into these non-sampling errors. So bias, this happens when we unintentionally word a question in a way that encourages the respondent there's a more desirable answer. So again, how many times have you been asked in high school about, do you plan on going to college? So if I ask that question of, what are your intentions for after high school? That's a non-biased way to ask the question. I'm saying, what do you plan on doing? You're going to trade school, you're going to go straight to work, you're going to take a year off, you're going to go to college, university, whatever it may be. Well, if I ask the question, don't you plan on going to college? I'm acting like there's only one path, which obviously I 100% disagree with. But, again, so if you make it seem like there's one right answer or you're trying to give a favorable outcome, it's a biased question. And that doesn't always mean it's intentionally biased. Again, oftentimes it's unintentional. Interview effect, we already kind of hit on. So again here, like if, again, it depends on the person who's asking you the question. If you ask questions face to face, so they're going to sometimes have an unintended effect on their response. Lurking variables, again, we kind of already touched on here. So example right here. If you're asking somebody a question and it's something that you can't possibly foresee. So if I was asking you guys, but you ask someone about, hey, how's life going, right? You might not know that they may have just suffered a loss of some kind, so their answer might be a little bit jaded there. Or, with students in general kind of thing there, you always got to understand there might be something going on that you don't understand. All right. For our example here, we're going to kind of walk through these next few slides, just kind of going through one large example of different sampling methodologies and how they might look. So once we conclude this, we'll be done for the day. All right, we have Jorge as a member of the student government at a large school with over 2,500 students. The student government would like to recommend that students with part-time jobs be permitted to get a class credit in business. Knowing that Jorge is a good statistics student, the student government asked him to estimate the proportion of students at the school who have part-time jobs. So first thing we're going to consider here, so the goal here is we want to show something. So we want to help kids who are working while going to high school get a credit out of it, right? Because if you're working, well, that's business experience, right? So they're trying to partition this so that way we can get it to happen. So again, to help these students, again, kind of get a little bit extra for their hard work. So the first thing we have to consider is what difficulties Jorge might encounter if he tries to ask every student about having a part-time job. All right, so like we talked about this one, whenever you have a very large population, by large I mean essentially anything over like 100, it would be really hard to interview every single person. So 2,500 kids, it would be really time-consuming for Jorge to try and talk to every single student. So again, we never want to try to do a census when we don't have to. Next one, Jorge is thinking of posting the question, do you have a part-time job on Facebook, and collecting responses to his post? He knows that not everyone will reply, but he thinks he'll get a large number of responses. Explain why, even if a large number of people replied, even as much as half the student body, Jorge would be unwise to suppose that the proportion of people of all who posted that have a part-time job is the same as the proportion of all students. So again here, it's not equally likely for everyone to participate. Therefore, it's not random. In the same sense, it's convenience because it's only his friends, and it's a little bit volunteer because, again, they're choosing whether or not to reply. So this would not be representative of the school, and therefore not a great approximation. Plus, if he's in stats, right, he's probably an upperclassman. So therefore, he may not know a lot of freshmen. So again, there's just a million ways to say this is not the best way to do it. Jorge is on the football team at his school and is thinking of asking everyone on the football team if they have a part-time job. Why might this give him a poor estimate of the actual proportions at the school with part-time jobs? So our answer for this one, that would not be representative of the school as a whole because you're only asking people on the football team. And again, a poor estimate here, it would probably be lower because, again, it's a convenience sample there. You're only talking to a certain group of people that are around you a lot. Therefore, again, so if you're playing a sport, you're probably not working as much during that season. All right, we're considering standing behind or beside a door at an exit of the school on the day after the last day of class is over and asking every student if he or she has a part-time job. How might this method produce an inaccurate estimate of the actual proportion of students at his school with part-time jobs? True. So, certain people might not be leaving at the same time, right? Seniors, you guys are famous for somehow working out those cool early release schedules. You don't have 7th or 8th period. First off, I need to figure out how to do that. Second off, so you might be gone. If I had a full schedule that day and I walked out to interview you guys, first off, some of you might not be here. Second off, who at the end of the school day wants to participate in a survey? Right, nobody, really? No one's going to be like, all right, school's out. Now let's go answer questions about school. That's not ideal. Also here, Jorge is one person. He's standing at a single exit of the school. Does every one of you take the exact same exit? No, right? People go out all kinds of doors. So again, not everyone has an equally likely shot. Now, if he advertised it and said, I'm going to be at this door on this day, please exit this way. So if you could guarantee everyone was coming out, it's a little better, but again, it's not ideal. Well, we've officially covered all the ways in which we could fail to generate a representative and random sample. So the key idea with samples, if you have a good sample, assuming, again, we have enough people involved, which we'll talk about those rules later on, basically, there's going to be like a set number. It's, if we have a proportion, we do it one way. If we have a mean, it's a little easier. Again, the idea here is that you want it to be big and then be two things, representative and random. So random means everyone has an equally likely shot. Representative means you pull enough people so that your sample looks like the population, so it obtains all the characteristics, all the different demographics involved. So what are some ways, and again, we'll answer this one as a class. I'll stop videotaping because I know you guys just love this. Our goal here, think of different ways right now we could generate a representative and random sample. So it doesn't have to be in this scenario, just in your school. If I asked you to do this, how would you pull that sample? Alright, so starting with our examples today, we are going to just categorize with those 6 different sampling methods we talked about. So for our different examples here, our first one, we have ask every 10th senior that walks in the door. So we see that we're at a centralized or a specific location. In this case, it's a door. And it's saying every 10th. So as soon as we see a descriptor such as every 5th, every 7th, every 9th, every 10th, whatever it may be, that's going to get an example of systematic. So no matter how long the descriptor is, as soon as you see that it's every 10th or every whatever if person, again, that's going to be a good example of our systematic. Okay, our next one. Randomly draw 50 names of seniors from a tub. So here, assuming everything's put into some type of thing, bless you, whether it's a randomizing program, everyone has an equally likely shot. So this would be a random or simple random sample. You could abbreviate that as SRS. Ask only all of the students in Monzo's English classes. So here, we're looking at a specific set of classes. So a couple different ways this can go. So take a minute now, kind of think about that, decide if that's grouping, if it's convenient, kind of read through it there. So, in this case here, since we're looking at English classes, so now admittedly I would probably extend this one on a test to be more specific to you guys, but since we're going over it together, in this scenario our grouping is looking at only English classes. So here we have our student population, or our population of any group, broken up into different groups. So since we're only looking at English classes, and we're asking all of the students in those certain classes, this would be an example of cluster. So my grouping is the classes, and it says we take all of the students from only the English classes that are taught by Ms. Monzi. So if it said take someone from each English class in the school, but the key idea here is that we're looking at all students in only those groups. Our next one, pick 10 students from each Algebra 1 class in the building. So here we see our grouping similarly done as by Algebra 1 classes. So here we're breaking up our students into all the different Algebra 1 courses, and we're only picking 10 from each one. So since it doesn't tell us we're picking all of those groups, we're taking some from each. This is going to be a stratified sample. Ask all of the seniors sitting in the cafeteria during period 4. Here, we're in the cafeteria, we happen to be there, and we're just asking everybody there. So again, this would be our example here of a convenience sample. Because again, it's just where we happen to be. We're asking everybody there. There was no thought going into it ahead of time. So if it just happens to be in a given location at a given time, it's what's easiest for that person. Plan an announcement and ask people to come take a survey. This would be volunteer. Because again, there's no selection process involved. It's just saying, would anyone like to come and participate? All right, and the next one here. We wish to determine what percentage of students would vote for a given candidate at Joliet Central High School. Assume the population is 3,000 students, and we would like a sample of 200 students. So we're going to work through right now a couple different methods for doing this. So we're going to use through stratified, a systematic, a cluster, and simple random. So this is similar to the types of questions you can expect to see in the short answer portion of your test. So I'm going to go ahead and pause for a second here and get something open so I can type, because we know my handwriting's not the best. All right, so we have stratified, systematic, cluster, and simple random. So I'm just going to abbreviate that as SRS just so you guys get used to seeing that. Oh, oops, didn't mean to press that. All right, so basically things we're looking for here. So similar when we've talked about describing valid sampling methods is we need to talk about how we're going to use that technique. So you're showing me the sense of vocabulary here with each of these, as well as you're telling me how it's going to be random, so everyone has an equally likely shot, and representative of the school's population as a whole. So in this case, we have 3,000 students in the school, give or take, and we want a sample of 200. So let's start with stratified. So for a stratified sample, the first thing we need here is we need some type of groups. So I would first throw some bold text in here so you can see vocab versus answer. So again, for stratified and cluster, I need to see that you have some type of grouping methodology. So again, that's something you can start with. There's no like distinct algorithm to answering these questions. It's just how I would set it up first. So I would first group students by. Now, this is where you can kind of think about different ways you could do this. So we've talked about grouping by maybe different floors in the building. We could group by different grade levels for stratified because we're going to be taking some from each. You could group by different electives, different whatever you want. So as long as you see that there's a logical pattern to it and that you're not only picking a certain, you're not giving any group preference, you're good to go here. So I would say I'd group by students by floors in the building. Or we could say by lunch periods. I kind of like lunch periods. By floors, so let's go by lunch periods. Or you could say floors in the building. Either way is cool. So you're showing me that there's grouping involved. Next thing we need to do is talk about how we're going to get them. So let's go with we need 200 people, right? So let's say I have we have 4 lunch periods, right? So 4th, 5th, 6th, and 7th, right? So 4 different hours that people go to lunch. I could take 50 from each. Then I would take 50 students randomly from each of the 4 lunch hours to get my sample of 200. Oh, sorry guys, had its control save there. So you've explained how you're going to group them and how you're going to get those samples. So those are kind of the key ideas there, is that you're showing me that you have a methodology for it. You know the vocab because you're grouping. And you're talking about how you would get them. All right, now we described how we're getting it, so now you need to explain to me, again here, kind of how you know it's representative and how you know it's random. So this sample, spelled sample wrong, is representative since all grade levels I'm trying to think. So we could be super specific here. If you were doing like a formal statistical study, you'd want to actually explain like all grade levels, including all demographics, blah, 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 blah. But I'm cool as long as you kind of give me that all grade levels are hidden. So all grade levels and all other demographics. Oh, spelled that wrong. Are equally likely to be in any lunch period. So it's representative because, again, you're saying that every lunch period has all different kinds of people in it. It's not like, only freshmen go during 4th period or whatever it may be. The next piece here, so talking about how it's going to be random. We used the word random here. So we made our groups, and then we randomly selected them, so that's kind of implied. So the words I should see in there, I should see some variation of the word random being used, so I know that it needs to be in there. It needs to be a random selection. And then, again, just talking about how it's representative and your justification for that. So that's about as long as you need there, 2-3 sentences. Doesn't have to be an essay. But again, just some thought put into it. All right, looking at our systematic example here. So the key idea here in the word, I need to see every 10th, every 5th, every 20th, whatever word you choose. So thinking about a good location in our building would, like we kind of referenced before, maybe being the main entrance. So I would survey, question, ask, whatever you want to use there. So I would survey every, let's go, 10th student that entered through the main entrance before school. So it's systematic, so you're saying a location where you're doing it, and how often you're going to survey or ask your questions. I get thrown there until I reached my sample of 200. So again, keep pressing that Control Save. So until you reach your sample size. This is random since all students have an equally likely, I'm spelling terribly, likely a chance of being surveyed, and representative because all students utilize this entrance. So again, it's random because it's not like we enter in grade level order, and it's representative because, again, everybody's coming to the same place, so all different demographics, all different grade levels, genders are all represented in this common place. Alright, so we got clusters. So another one that involves grouping. So I'm going to start with, I would first group students. So you have to be careful with the way you group clusters. Stratified, you can pretty much group anyway. And then, because you're pulling from each group, so you're good. With cluster, remember that we're only going to take certain groups. So this is an example when you definitely wouldn't want to group by grade level. So you can use grade level for stratified. You definitely don't want to use grade level for cluster, because then you would be excluding entire grades. So here I would suggest keeping with these by periods, or by lunch periods I should say, or floors in the building. Just because, again, those are kind of like very good ways of grouping without necessarily limiting who's in your groups. So here, again, then I would only select, so you could say certain lunch periods, or certain floors. So whichever one you chose. And again, now we just need to get back to how we're getting our sample. So we picked certain groups, and so we're going to and ignore the others to obtain my sample of 200. So you're explaining to me that you're only looking at certain groups, and you're going to ignore those others, so that's a good cluster sampling to obtain my sample of 200. Then again here we need to explain kind of why it's random. So, students all have an equally likely chance since lunch periods are randomly assigned and are representative since, again, since they are not organized by grade level, etc. So again, etc. is cool in these because, again, like we all know that lunch periods aren't broken up by like grade level. So again, as long as you're kind of using those keywords to me that explain why it's random, why it's representative, we are good to go there. Alright, this one is the easiest one. That's why we saved it for last. So simple random sample is basically you just tell me some type of methodology where all students in the school have an equally likely shot, and you give me a way you're doing it. So first, I would obtain the school roster from, let's see, pick an administrator, or you could say teacher here, or whatever it may be. So you're in some way or form, it doesn't have to be 100% plausible here, just give me some kind of idea showing me that you have everyone's name. And utilize Excel, that one works, to randomly select 200 students from the roster for my sample. It is representative since all students are in the roster. In this one, we already talked about how we're randomly selecting them, so there's no need to reinforce the idea of randomness there because we already talked about it. So simple random sample, pretty much the easiest one to say. You could literally always talk about a hat if you wanted to when defining this one. You'd say, I would put all students' names in a hat, or you'd say I'd use a random computer selection program, or you can be specific and say, because Excel does that. That one's the easiest one to answer. Admittedly, the two that require the most thought are going to be stratified and cluster because you have to talk about how you would group. Systematic, just talk about a location and then how every 5th, every 10th student, and simple random, pretty easy there. Alright, so moving forward. Okay, we'll go through these. I actually just wanted to get that one example in there because I know these are kind of long to think through. So we had a couple different ones here. So let's actually switch the order around a bit here. So we'll start with examples. Let's see here. 9 and 10 we will go through as a class tomorrow. We'll get through one more slide today though. So here, removing bias and lurking variables. The key idea with these is that we want to try to take away any type of strong wording or how things can kind of overlap. So just looking at these questions, we'll notice here that there's a distinctive tone to them. And again, it's just an idea that bias implies that we're eliciting that there's a preferable or desired response. So the first one, imagine that you're surveying somebody and you think that these questions, would they make sense? So the government should force you to pay higher taxes, right? Now, key idea there, I'm implying it's the right answer, so I'm saying like, right, we should do this. Also, I'm using really strong words like the government should force. Now, if I wanted to ask this question without bias, perhaps I would say something like, would you support an increase in taxes? And now ideally, when you're giving things like this, anything that involves numbers, you want to be as specific as possible. So if it's a 0.2% increase, if it's a 1% increase, you should never vaguely ask questions. Any good reporting, any good surveying, always as specific as possible. If you're vague in your questioning, it tends to be that you're showing a lot of bias in there. Our next one, how would you rate the career of legendary outfielder Joe DiMaggio? This one, you're asking an honest rating, but you're using the word legendary. So even if someone doesn't know who Joe DiMaggio is, you're implying that they should rate them very highly because you're using the term legendary there. So cleaning that one up, pretty much just take out the word legendary. Next one, what suggestions do you have for improving Tom's tomato juice? You can tell this is a textbook question because I don't think anyone's ever heard of Tom's tomato juice, but nonetheless, key idea here is we're asking them to improve upon it. So if you're saying it needs improvement, by default you're kind of saying it's already not very good. So this would be better if I wanted to find out a rate. I said, on a scale of 1 to 10, how would you rate Tom's tomato juice? Where 1 is the worst, 10 is the best, whatever it may be. Many people have said that there is a need for stricter laws on dangerous weapons. Do you agree? So this is kind of similar to number 1 in the sense that, A, it's a question we hear all too common, and especially, in our media and everything, we're hearing a lot about these different things here, and this is not a good version of it. So because it's not specific, it's saying need for stricter laws. What exactly does that mean? So again, stricter is a pretty vague term. We don't have specifics there. And then it says dangerous weapons. Again, harsh, biased wording. You're essentially saying, like, if you don't agree with what I'm saying right now, you're evil, you're bad, you're wrong. Because again, I'm telling you they're dangerous. So again, if this was a specific question here, you'd want to take out the idea of stricter laws. You need to explain what laws you have in question here. And then instead of saying dangerous weapons, be specific in terms of what are you talking about. So again, anything vague always has high levels of bias. Next one here. Should we reduce violent crimes by getting guns off the streets, or should we just lock people up longer? Now, this is another one where, again, it's very vague. It's clear that they're only giving you 2 options. So they're not explaining how they're going to do it. So this kind of goes in tandem with the last question here. So it's not talking about an actual methodology. It's kind of just very biased in the sense that they're giving you an ultimatum. You either do option A or you do option B. So again, any type of these questions, it's just you're not And that too, should we just lock people up longer? That's not specific at all. What does that mean? So what, everyone who's got a 6-month sentence now stays perpetually? Like, we don't know. So again, in terms of a lot of these questions, you want to make sure that you eliminate bias, be as specific as humanly possible, and any type of strong words like lock people up. Like, again, there's another way to say that to remove any type of negative or positive, whatever you may think of it as, connotation. And again, use plain, basic words. So that way you're not indicating a preferable choice. And the last one, smoking is okay as long as you don't smoke around people that mind. Again, it sounds like more of a statement than a question even. You're basically telling them, like, yeah, like, you agree with this, right? And again, you're implying there's a right answer. So if I was going to ask this question without any form of bias, I would say, what is your opinion on cigarette usage in public? So you leave it kind of open-ended. You let them elicit their response. You don't imply, here's an answer. So again, we'll start off class tomorrow with our other 2 examples here, 9 and 10. So we'll kind of work through those together on the board. And then we will conclude our last 4 slides here, or last 5. My bad, I'm counting there. Either tomorrow or Friday. All right. What's that? We are on slide 30. So we got 30 through 34, so 5 slides. All right, so today the last thing we need to talk about in this unit is going to be known as experimental design. So this is kind of a specific case here. So we talked earlier about doing experiments versus a study, or an observational study. So the difference here is once we've chosen an experiment, we have a little more to think about. Because a study, pretty much you're either looking at data that's already been collected, or you're just, kind of watching something and recording what happens. There's much less thought involved in that, I guess you could say. Not necessarily thought, but procedural things. So once we've chosen to do an experiment, we actually have 3 different types that we're going to cover here. So the first one here in our experimental design is known as randomized. So this is a completely randomized experiment, is one which has a random process is used to assign each individual to one of the treatments. Now, the key ideas of this, there is only one treatment. So good examples of this are when you're dealing with medical experiments, so such as a treatment, say, for the common cold. So I've come up with some new formula that I think is going to reduce and cure the common cold, and I'm going to go ahead and test it. Now, randomized just means this. So let's say my sample is all of you people in this room, and you all have the cold, right? So I would gather a group of people experiencing cold or flu-like symptoms. Therefore, they're all in the same area, which is a lot of you, apparently, with the coughing. But concept is, you are my sample. Now, how I'm going to compare this, whenever you're doing these studies, you want to work with what's known as a placebo. So how many of you actually know what a placebo is? Wonderful, right? Solid. I'm glad those of you in psychology. So how it works, a placebo is this. There's been countless studies over the years that have shown your mindset going into something has a huge, huge effect on how your body responds to it. So that's you could read whole self-help books on visualization. The concept is that if you believe something's going to work for you, it's more likely to actually work. So there's been a fairly decent correlation shown that people healing from placebos. So basically the way it works is this. Now, if I wanted to do that experiment, right, so common cold, I would randomly, so randomized means I put all, so it's similar to a simple random selection, right? So I got my population of people. Now I'm going to randomly sort you into 2 groups. So the key indicator of a randomized design is there's exactly 2 groups. It's definitely something I'd write down. Because when we're trying to determine from a word problem which one we're working with, that's the big indicator. Exactly 2 groups. One group gets a treatment, so it might be a pill, it might be a shot, whatever it is. It might be a program that they're going to go on. So for dieting, you might have to follow a certain strict diet to see the results of it. The other group gets what's known as a placebo. So the easiest way to think about this is that you have 2 pills. They look identical. One has the treatment or the medicine in it. The other one is what's known as a sugar pill. So it's a placebo. So that's to rule out the effects that the benefits of the new treatment are just from goodwill or from the power of the mind over the body. I know that sounds kind of metaphysical, but that's actually what you got to do. So that's the way it kind of works there. So again, it's just to compare the results. Okay, this is my control group. So you have a treatment group, gets the treatment, and the control group gets a placebo. So you can compare the effects side to side. Yeah. every single major medical study utilizes one of these methodologies here, and that's kind of a standard. So remember in like biology when you guys did experiments, you had different groups, right? One, you always had a control group. So if you were trying to study like different things that you could feed plants, like fertilizer versus one or the other, there's always that control group, which you just give nothing to, just so you have a baseline to compare it off of. So randomize, 2 groups, one gets the treatment, one does not. All right, next one here, we have randomized block. Now, I'm just going to call this one block. So you have randomized and you have block. The main reasoning being is because otherwise they both have the word randomized in them, and that can become a bit confusing. So we have randomized, and then we have block. So in a randomized block experiment, individuals are first sorted into blocks, and then a random process is used to assign each individual in the block to one of the treatments. So, key idea here, the difference between these two. So the first thing I noticed, randomized has a single treatment. Randomized block has multiple treatments. So, single versus multiple treatments. Actually, let's realize it's a typo right here. Let's go ahead and delete this to the treatment. My bad. That's what happens when you copy and paste a little too much. So randomized block, a single treatment is being compared, or randomized has a single treatment. Randomized block has multiple treatments. So here, this is kind of similar to our stratified and our cluster sampling, but we're going to put a little more into a design here. So I'm going to kind of randomly put people in these different blocks. So here I might have 100 participants, right? I'm going to draw this on the backboard to make a little more sense for you guys. All right, so let's say I have 100 participants and I want to use a randomized block design. So I decide, okay, 100 is divisible by 4. I'm going to have 4 blocks. So I'd use a simple random sample, name picker, giant hat, whatever you want. And I'm going to throw 25 people in each of these blocks. So they've been randomly assigned. There's no preference. It's not grouped by grade level. It's not grouped by age. So kind of yesterday how we talked about that default way of grouping is you just basically say, I'm going to randomly sort people into 5 groups, right? So that's why I did it. Randomly sorted people into 4 groups. Now, to make it the block design, I'm then breaking up these. So let's say I had 2 treatments I'm working with. And I wanted to compare which one's going to do better. In every medical experiment, you always need a control group, or that placebo group. So I have 2 treatments. This means I have 2 groups plus my control group. So what that means is I need to take each of those blocks now and split them up into 3. So 25 is not divisible by 3. Sadly, I should have picked a better number for this example, but doesn't matter. They don't have to be exact. So now each one of these is going to be broken down into 3. So in each of my blocks, there's going to be treatment 1, treatment 2, and a control group. So I have treatment 1, treatment 2, control. Now, if I was looking at a word problem and I was comparing just these 2, so randomized versus a block, which word problem do you think is going to be significantly longer? Randomized block, right? That's a lot of groups. So if I'm reading a problem and all of a sudden it's talking about like, okay, so we're going to divide it into this group, then I'm going to create subsections and then, divide by age. Like, if there's a giant explanation of just creating the groups, you can immediately identify that it is randomized block because it's a really long explanation. Like, think how long it took me to explain this to you guys, right? Drawing stuff. They're going to be the longer problems. So if there was a multiple choice thing and the problem's yay big, it's probably randomized block, right? There's a giant explanation with it. And we're not going to analyze it yet. I'm not going to have you do any math or anything and calculate which treatment's superior. We're just worried about understanding which one it is. So randomized block, you have multiple treatments and a bunch of groups. So there's a bunch of grouping. There's a description. You break it into blocks, and then you kind of further divide those blocks up. Last one, which is going to sound way different than the rest. It doesn't have the word randomized in it, so that's a plus. This is known as match pair. Here, there is only one group, and every member receives the same treatment or treatments. So this one, it can have either a single or multiple treatments being applied. but the key idea is everybody's getting the same thing. Also, this one involves a pre and a post test to compare results. So think of like longitudinal stuff, like I don't know, I'm gonna go, okay, so like a weight loss program. If any of you have ever like actually looked into that, whether you're in like a certain athletic class in our school, whatever it may be, is like you can't lose 20 pounds in a week. Like mathematically, that doesn't happen. So what you would look at here is like, okay, if we're going to study this concept, we need to look at what happens. We're going to give them a regimented diet. We're going to give them some form of supplementation and then exercise. And we're going to compare it over a year-long period and see what the results were. So all the people participate, and then you kind of see, okay, if it worked better for this person, if it worked better for that person, what may have happened, what could have occurred, and you record all that data. So it's a longitudinal thing. The rest of these might be like maybe a week kind of thing, maybe a little longer, depending on how severe the treatment is. Like if it's for a common cold, and I was doing a block or a randomized, I would probably say like a week. You should probably knock that cold out. Now, if you were testing something more, high stakes kind of thing, like a cancer drug, maybe that is a 6-month period. But match pair, you're always going to kind of see those longer time periods, and it will identify a pre-test, so examining before and examining after. Okay, so looking at some examples here. One more bit of vocab. These ones are easy because you've been doing them since at least freshman year in biology. Explanatory versus response variables. So our first one is an explanatory variable. This is our independent variable. So if you're thinking back to Algebra 1, this is x. So if we have y equals mx plus b, right, this is our x variable. In the case of statistics, this is the treatment we are applying. So we control how much we give. We know who's getting it. That's our explanatory variable. So that's what's going to be our independent there. Now the response variable, this is what we are measuring, or our dependent variable. It's a consequence of the treatment being applied. So the treatment is always your independent, and then your dependent, which is your response variable, is what you measure at the end. So if we were talking about that weight loss thing, it would be how much weight was lost at the end. If we were talking about the common cold, it's about how much your symptoms were reduced or eliminated. If whatever it may be, so whatever you're measuring, if it was that crops problem, right? So if I was talking about fertilizer testing, the fertilizer is my treatment, so that's my explanatory variable, which fertilizer I'm giving. The response variable is whichever crops had the best yield. So for those who don't know about farming, yield is just how much it produces, right? So treatment, what you give, that's our explanatory. What you measure at the end, that's your response. All right, so we're going to go through a couple of these examples here and answer these questions. All right, so for our first one here, we have a drug company wants to test a new medication for bodybuilding. As you can tell, I wrote these problems. The researchers found 200 adults aged 18 to 24 and randomly assigned them to 2 groups. The first group received the new medication, while the second received a placebo. After 2 months, the percentage of each group whose lean muscle mass increased was recorded and compared. All right, so getting into answering these 4 questions here, I'm just going to copy and paste them. All right, so for the first one, what kind of experimental design is this? Well, we've seen we have 1 treatment and 2 groups. Spelled treatment wrong. Where do we start? Treating. All right, so that's my first indication there. So I've seen 1 group is getting the treatment, 1 group is getting a placebo. When we see 1 treatment in 2 groups, this is going to be randomized. There. Debating me on how to spell. Okay. Oh, why that? Yeah. Oh, I put 4 dots. That's why. Okay. So 1 treatment in 2 groups, so we're randomized. What is the population being studied? So this is another example of these kind of more drawn out questions where we have to look a little bit more. So population versus sample, right? Sample gives us a specific number of people involved. Population is the larger group or the section we are looking at. So, what would be our population here? Adults aged 18 to 24, right? That's what's cool about computers. You can copy and paste. You should be able to copy and paste pretty much every population that's given in a problem. So here, adults aged 18 to 24, that's our population. Next one we got, what is this sample being used? So the sample is as specific as we can be. It's going to be a number of people in the category. What do we got? Right, the 200 adults. So it says right there, 200 adults were our sample. So 200 adults, age 18 to 24. Now, as we move on, we might see problems that aren't as specific. They might not give us the exact number. So we'll kind of go to a default answer for those. If I didn't give you the exact number, you would say the adults who actually participated in this study between ages 18 and 24. All right, last one. Potential lurking variable. So we talked a little bit about this earlier. A lurking variable is something that we can't really control or that we can't account for, but it could affect it. So if we're thinking about this right here, so basically we're saying, okay, they're going to take this medication. How many of you have been sick before? Probably everybody, right? Unless you're a vampire. Then you probably haven't been sick. But also very unlikely. So if you're given this prescription by a doctor, are you guaranteed to take it every single time exactly on time? I mean, if you're like this awesome human being, yes. But me, I know for a fact that I've had, like, okay, you got to take this every 12 hours, and you might take it every 10 or every 14. You might be busy and forget. Same thing here. People aren't always going to stick to a routine. So a lurking variable here, people might forget to take the medication or halfway through choose to quit. What's that? Or perhaps they are allergic and stop for that reason. So all of those are good answers. I only need one on the test. So you could just tell me they might forget to take it. Or you could say they might choose to quit. Or you could say they might be allergic and stop. Or another lurking variable, right? Maybe someone has really good results, but they also did something else on top of this. So maybe just instead of taking the medication, they decided to, work out a lot, or they decided to really eat healthy. So there's a lot of things that can kind of go together here. So basically, a lurking variable, you're just telling me, how do you think things could go wrong? Or what could be an outside factor that we can't really measure? All right, I'm going to leave this up here for a second if you guys want to copy that down. All right, we can go ahead and get rid of this and move on to our next one. 2 more slides to go, guys. I know it's been a long one. Okay, a farmer wishes to test the effects of a fertilizer on her wheat field. She has 4 equal-sized plots of land, one with sand, one with rock, one with clay, and one with average soil, so a mix of those 4. Or those 3, I should say. She divides each of the 4 plots into 3 equal-sized portions of land and randomly labels them 1, 2, and 3. The 4 1 portions of the land are treated with her old fertilizer, so that's like her control group to see what's already been happening. The 4 2 portions are treated with the new fertilizer. The 4 3 portions are treated with no fertilizer. At harvest time, the wheat yield is recorded for each of these section of land. All right, so what kind of experimental design is this? We've seen it's a very long explanation. We've seen what we might consider excessive groups and multiple treatments. Whenever we see those 2 things in combination, we have randomized block. And again, on a test, I would be cool with you just saying block. I'm just being, as correct as possible here and throwing that word randomized in as well. Next one, what is the population being studied? Now, this is where a variety of answers can come into play here. So this is a problem where it wasn't people, so sometimes it's harder to define what our population is. If we look back here, what is it that I'm studying? So different soil types, right? What am I growing? Wheat, right? So we're growing wheat. So what she's studying is what best helps that wheat grow. So the population here would be wheat. Or if you said crops, like if you told me crops here, if we said like crop fields, I would be cool with that too. So either one of those, totally fine by me. Wheat is technically the right answer, but crop fields would also be cool. All right, on to our third one. What is the sample being used? Now, there's a couple ways to answer this one too. The most general would be her wheat fields, right? Because that's what we're looking at, but she gets a little more specific. So here we see she has 4 equal-sized plots of land. So that would be my samples. So the 4 equal-sized plots of land, that's where she's actually doing her experimentation on, right? So one with sand, rock, clay, and average soil. So we have a couple different environments we're looking at here. That's why she utilized the block, because there's some other things she wants to look at. So if we go ahead, we can throw that in here. Okay, thank you. Yes. So here we have 4 equal sized plots of land, one with sand, one with rock, one with clay, and one with average soil. If you just gave me this part where it just says 4 equal sized plots of land, or her 4 equal sized plots of land, that would be acceptable too. But this would be about as big of an answer as we're looking for there. Oh, my bad. Let's save. All right. So we got through population, we got through sample, and now we're looking at explanatory and response variable. So again, explanatory is the treatment we're being applied. It's our independent variable. And then we're looking at the response variable, so what we measure at the end. So what is it? What is the treatment, or what am I putting on these crops here to see what happens? Fertilizer, right? So it says we have our old fertilizer, a new fertilizer, and then no fertilizer. So our explanatory variable is going to be the fertilizer. So that's what we're controlling, right? I'm deciding which place gets it, how much I put on. The response variable is what we measure at the end to determine success. So if we're growing wheat, what am I probably going to measure at the end? Yeah, the yield, or how big it gets, right? So it says at harvest time, the wheat yield is recorded for each section. So the wheat yield, or if you want to use other words, you could say how much the wheat grows, whatever. Again, any synonymous terms are cool there. So I'm going to pause for a second, guys, and go ahead and get that down. Okay, and last slide here, last example for Unit 1. We have some people who race greyhounds give the dogs large doses of vitamin C in the belief that the dogs will run faster. This is 100% from a textbook. I didn't even make this up. Investigators at the University of Florida tried 3 different diets in random order on each of the 5 racing greyhounds. They were surprised to find that when the dogs ate high amounts of vitamin C, they ran slower. So, first thing here, I have 5 dogs in my group, right? And they're all doing the same thing. So they're all, and again, this one, in matched pair, you can either have one treatment or you could have multiple treatments. It doesn't matter. The key indicator here is that we have one group only, and they're all doing the exact same thing. So for this one, our experimental design is going to be matched pair. So here we have one group. They all get the same treatment or treatments. So in this example, it's multiple treatments, right? Because we see here that it says they try out 3 different diets, right? But they're all getting it. So it's not saying I'm grouping that one dog gets this, one dog does not. They're saying all 5 of the greyhounds, they try all 3 of these things, and we see which one works best. So our pre and our post test, right? We knew how fast the dogs ran before. Now we're going to try these 3 different diets, see which ones work the best. So again, one group, they all get the same treatment or treatments, and that gives us match pair. The next one, what is the population being studied? And we're looking at the sample right after, so those are easy to kind of do together. So, population here, we're looking at racing dogs, right? So, greyhounds, right? Or racing greyhounds. You could just say greyhounds. I would be totally fine with that. So our population is either racing greyhounds, or if you just said greyhounds, again, totally cool with me. Just try to be specific with the type. Don't just say dogs or animals, right? It says greyhounds, let's use the words. Now, this one, it doesn't give us a literal type number, but they use the number in words similar to the last one here. So the sample being studied, we have 5 racing greyhounds. They're the ones involved in this. They're in our sample, so that's what we have there. So we have 5 racing greyhounds. That's who we're actually doing these various diets on. All right, next 2, explanatory and response variables. So explanatory is the treatment that we're applying. So the treatment I'm applying would be 3 different diets. So it says in a random order, we're trying these 3 different diets on the dogs and seeing which one of these diets improves the way the dogs run. So for our explanatory, we have the 3 different diets. And again, how we're determining success here is how fast the dogs run. So what we would measure is the racing times of the dogs. So you could say the racing times of the dogs, you could say how fast they run, how well they do, whatever it may be. Those are all synonymous to me. And obviously the fastest or the best time would be ideal. Alright, the last bit here. We have, what is a potential lurking variable? So, real quick here. So again, whenever we're working with animals, we can always just kind of assume that they can't tell you how they're feeling. So, they might be sick. They might be hurt, etc. All of these could affect their performance in the race. So again, anytime you're working with animals, just explain to me how they can't tell you how they're feeling, right? So you might use the wrong version of effect. I did. Okay. So it could affect their performance in the race. So there, again, like maybe that dog rolled its ankle or slept funny and it's sore that day. You don't know. All right, so this is the conclusion of all the notes for Unit 1.